basic platform. HD means high definition. So first of all, what is virtual prototyping? Virtual prototyping is the process used to computationally test the product before committing to actually making a physical artifact. So what are some aspects of it? Why is it good? It has animation, you can do graphs on it, you could estimate the lifetime of a product, and the benefits are the testing while the design is in process. You can detect the flaws, you reduce the cost and the time that you do this product, and you get better quality from it. What are the goals for this summer research? There's three things to do summer research. First, we want to get used to working with this software to get good at it. And then the three things that we did was the mathematical analysis. Then we build the virtual prototype in software, and then we test it. And we compare the mathematical results to the virtual prototype results from the software. So these are the three steps that we did before going to our final project. First, we did a pendulum system right here. Then a RAM system, then a 4-by mechanism to go to our final project right here. This is the pendulum system. So here we see the CAD model that we did in SolidWorks. Then these are the equations that we got from for the motion equation of the pendulum, the motion acrocyclic that you guys saw previously. And this is the graph that we got actually from SolidWorks. So this is from here we can get the period of it, and then this is the mathematical calculations of it. So here this is the percent difference, and we got a 14.9%, which is not good because if it's not under 5, it's not considered accurate. Therefore, we looked at what could improve, and then we looked at this thing and we saw it's not a simple pendulum. A simple pendulum is just a string with a mass attached to it, but this pendulum actually has a mass to this thing, and then there's friction between them two, and then this has a mass also. So that's why we changed our equation. And now we got 0.52 seconds. So now our percent difference is 4.6, which is good because it's less than 5% difference. Now we move on to the 4-bar mechanism. This is the 4-bar mechanism. This is the base, which doesn't move, and then all of these move. These are the initial parameters that we were given. This is the length of the rod. This is the first initial angle that you guys see over here. And this is the position of this output link, the last link. These are motion equations that are probably complicated for you guys. We're not really going to go into it, but we did all of these equations to come up with our results. This is a program, it's this data that we got from a program, Maple, that we created. And these are the results for position, data, velocity, omega, and then alpha is angular acceleration. All of them are angular quantities. And then we looked at, if we want to know the torque profile, then we look at these general cases, which we're not going to go into again. They're really complicated. They're for like a 412 MA course, so we're not really going to look into it. And you can skip that one. So from the simulation results, we got these three graphs, which is the frequency of the output length. From this one, we can see the frequency that we inputted was 10 hertz, and the frequency that we obtained period of this graph is 0.1, so the frequency we obtained was 10 hertz. Same thing here, 0.05, so the frequency we obtained was 20, and the input was 20. But then when we went to a higher frequency, we see that we have a percent error, 1.01, because the frequency is higher. So as you increase, then the software has some kind of error that we have to account for later on. So then we move on to RAM systems. This is the CAD model. This is the mathematical analysis that we did with velocity that comes from the energy equation. And this is the percent difference that we find from these calculations and these results that we find from SolidWorks simulation. Which this is the graph of displacement versus time, which gives you velocity. This is the slope of it, and then that's what we plugged into our calculation. It's 4.28, which is less than 5%, which is good, but we wanted to see if we could improve that also. So we looked at, we see that it's a cylindrical system, so SolidWorks has to iterate a lot more times to get the path and the velocity and all the quantities from it, because the cylinder touches the ramp at a lot of points, like you guys can see over here. And then that's why we looked at the sphere, which only touches it at one point, and now we're going to do the sphere calculations. So here is the spherical model, these are the calculations, and then this is the graph, the slope of it. for the velocity, and then the percent difference was 1.26%, which is the lot better. So how does that help us? A real car has cylindrical wheels, but what we can do is use the cylindrical equations, but at the same time simulate it as a sphere in SolidWorks, and that would be a lot more accurate. Now we move on to our final project. What was my final project? It's called HD2 High Definition Haptic Device, which is a haptic platform that you could touch it and it will move in 5 degrees of freedom. You touch it in 6 degrees of freedom and it will move in 5 degrees of freedom, and it lets you interact with virtual environments. So these are some of the parts of that haptic platform that I built. So you guys just can see it. They don't have names or anything, it's just the parts. So this is the assembly that I made, and you guys can see the planes. You can see plane, or it's plane, never mind. Yeah, this is the assembly. You can see the planes and everything. This is what I made in SolidWorks. And now we can see exported view. Can you play? We can see exported view of it, the parts, and how they come together to the assembly. And as you guys can see, it probably seems easy, but it's a bit complicated. So the conclusion is we just got to building the part, the model, but we're not done with the mathematical analysis and the comparison. So that's our next step for this final process. And the references, and then acknowledgements to our mentor, PhD candidate Lenfen, which is here taking a video, Suman, Sashi, BS students, Osaka, Chris, and Buay, which are our partners from lab. And then from the CSTEP team, Shana, Mr. Drexel, and Polaren, Mary, Matthew, and Michael. Thank you very much. Questions?
Good job, by the way. But you made mention of coming up with your own equations and stuff.
Yeah.
Is it questions that are already there for you to make adjustments to it to correct the mistake, or you started from the scratch, or came up with your own?
Start from scratch, and then pretty much you build down upon that with the knowledge that we've gotten from previous classes like statics, dynamics, things like that. So you know basic equations of motion like velocity, acceleration, things like that. So you can build upon those, like energy equations, and then from there get the velocity, mix them up, and then try to get things from there.
Were you assigned to make the entire platform yourself, or were you assigned to study the mechanisms that are going to make the platform work?
We were assigned to make it and then get as far as we could, because it's only actually for the lab research type program. But we were assigned to build it, and if we can, do the mathematical analysis, but we couldn't get to that.
So did you come up with all the mechanisms, like the full bar mechanisms?
Yeah, with all of the previous ones, yeah. Yes.
What is that mechanism going to do? So you said it was to explore environments. What would be an example of that?
Yeah, an example of it is in medicine. Like if you're doing an operation, sometimes the human hand is like too big or things like that, so you could, in a smaller scale and doing virtually, you could control that so that it can do it better. I was going to show a video, but
thank you.
yeah. Any more questions?